In this video, we're going to talk about polar presentation of complex numbers. So let's say we have the complex number z being equal to a plus bi. Presenting this on this graph, we have a to be here, we have b to be here, and we have r to be here. This is the length from the origin to the point that we have. Now, in this video, you're just going to focus on this diagram here, the right angle triangle here, and we know that it makes an angle theta. So let's just focus on this diagram, the right angle triangle, where here is our b and here is our a, making an angle theta. So we know that writing the theta in terms of a, b, and r, we're going to have cos theta should be equal to a over r, and sin theta should be equal to b over r. Making a and b the subject, we should get a being equal to r cos theta and b being equal to r sin theta. Very simple. Then we just replace a and b with r cos theta and r sin theta into the complex number that we have here. So we have this complex number z a plus bi. Replacing that, we should get z being equal to r cos theta plus r sin theta I. Then factorizing the r out, we should get z being equal to r multiplying cos theta plus I sin theta. Then we have this. Now, this is the rectangular form of the complex number, and this is the polar form of the complex number. Very, very simple. Now, sometimes too, the polar form of the complex number can also be equal to. So let's say we have the polar form, which is z being equal to r multiplying cos theta plus I sin theta. Now, this polar form can be equal to r then e, which is the exponential function, raising the power of I theta. This is also correct. Now, we can also write this polar form into algebra of complex number, where we have z being equal to r e, which is the exponential function, raising the power of I theta. Now we can identify r with the modulus of the complex number. So the r here, we can identify it as the modulus of the complex number, and theta with the argument of the complex number. So r can be identified. So the r can be identified as the modulus of the complex number, and the theta can be identified as the argument of the complex number. So with that, the angle just lies between negative pi less than theta less than or equal to pi. But since rotation by theta is the same, we can also present it as 2n pi plus theta, where n is any integer at all. So now let's just put this theta here into this equation here. So we will have z being equal to r e, right? Then our I into bracket 2n pi plus theta. Very simple. So the algebra of the polar presentation is different from that of the real and the imaginary component presentation. So the results are just identical. Now some operations prove much easier in the polar presentation. Others are more complicated. So the best presentation for particular problem must be just determined by the manipulation required. Very simple. So these are the things that you need to know. So let me just write them here. So you just need to know, first of all, Z can be equal to A plus BI, which this is the rectangular. So let me just go to another page. So Z can be equal to A plus BI. This is the rectangular form. And we have Z being equal to R multiplying cos theta plus I sine theta. And this is the polar form. And we also have Z being equal to R E exponent I theta. And this is the exponential function form. And we also have Z being equal to R E exponent I into bracket I theta plus 2n pi. And this is the algebra of complex number. Very simple. So these are the things that you need to know. In our next video, we are just going to solve some examples of how to present complex number in all these forms. So watch out in my next video. Thank you for watching this video. See you.